Okay, in this lesson, we'll be looking at something called law of sines. So our objective here is to apply the law of sines to solve oblique triangles. So we'll do a little review first. First, what an oblique triangle is. Oblique triangles are triangles with no right angles. Previously, we learned about acute triangles, obtuse triangles, right, scalene, equilateral, and isosceles. Here, we're just talking about triangles that have no right angles. So oblique triangles just have no right angles. Next thing we want to review is labeling triangles. If we had this triangle here, specifically this is intended to be oblique, no right angles. If we were to label the angles are always used uppercase letters to identify the angles. So we had the letters A, B, and C, uppercase A, B, and C. While the sides, we use lowercase. And the lowercase are always located opposite the corresponding uppercase angles. So if we had angle A, little a is on the opposite side, uppercase B, lowercase b on the opposite side, and uppercase C, lowercase c. You also see, in addition to regular A, B, and C letters used for angles, you also see Greek letters. So alpha is the Greek letter used instead of the angle A. There's the symbol for alpha, and we place at the angle where A is. So it's just a substitute. Second letter of the Greek alphabet is beta. Beta is used instead of B. There's the symbol for beta, and again, where angle B is. And the third letter, gamma. The symbol for gamma looks like a little y, and it's the substitute for C. So some other review. Previously, we worked on solving right triangles. Again, we'll be looking at oblique triangles. If you recall, when we had a right triangle and we had all three sides, A, B, and C, again, notice lowercase letters, we would use Pythagorean's theorem to help us solve if we were working with just the three sides. The three different forms of Pythagorean's theorem was our a squared plus b squared equals c squared minus a squared equals b squared, and c squared minus b squared equals a squared. Also, with right triangles, if we had one acute angle and two sides, this is where we would use one of our trigonometric ratios, whether it be sine theta equals opposite over hypotenuse, cosine theta adjacent over hypotenuse, or tangent opposite over adjacent. So we'll look at the law of sines, again used for oblique triangles. So if I had this oblique triangle here with sides A, B, and C, and angles alpha, beta, and gamma, the deal is right now, if we had drew this altitude, the altitude it's drawn from one angle perpendicular to the opposite side. The deal is, if we've got this angle here, gamma, we're going to create this ratio of sides here. So if I just looked on the left side and work with that right triangle, we would be able to use our sine ratio to help us determine the length of h, because that's what we're going to be doing. And so if we multiply b on both sides, we get b sine gamma is equal to h. Well, if I did the same thing working with angle beta, if I work with angle beta and I work with the right triangle on the right side, I can begin again to create this ratio. Sine of beta, again, would equal opposite over hypotenuse. The opposite is h, the hypotenuse is c. To solve for h, multiply both sides by c, end up with c sine beta is equal to h. Well, if I compare the left side says h is b sine gamma, and the right side also says h is c sine beta. That means those two can be set equal to each other. Well, if I divide both sides by b, and I also divide both sides by c, the b's will cancel on one side, c's cancel on the other, and what I'm left with is sine gamma over c is equal to sine beta over b. So what I'm creating is a ratio that compares one angle to its opposite side, the other angle to its opposite side. which means if I've got three angles, I could also presume that sine of angle alpha over A is also equal to these two ratios. So what we've created is the law of sines. The law of sines says the ratio of the sine of one angle to its opposite side is equal to the ratio of the sine of the second angle over its side, which is also equal to the sine of the third angle. If I was to use the non-Greek symbols, it would simply say sine A over A equals sine B over B, which is equal sine C over C. These three ratios could be rewritten as reciprocals. And so instead of having the angles on top and the sides on the bottom, I could have the sides on top, angles on the bottom. So just a different format. So of course I can use regular English letters. So the deal is, the left side, we typically use these when we're looking for a missing angle. So if we're looking for an angle, we put the angles on top. On the right side, we use this if we're looking for a side. So we put the sides on top. So when do we use law of sines? Well, first we use it. What must be given is an angle and its opposite side. That way we can begin to create that ratio. And one other measurement. So here's some different situations. So in the first situation, there's the acute angle and its opposite side that was given. Now if I'm given one other measurement, say I'm given a second angle. Then we have the situation you've seen back in geometry, side, angle, angle. The side was given its opposite angle and the corresponding angle, also known as SAA. Second situation, if I start with the angle and its opposite side, and if now the second bit of information is a side, here, back in geometry, side-side angle, or SSA. Third situation is a little bit different. Here, if you're given an angle, a side, then another angle, angle, side, angle, or ASA. It appears as if we don't actually have an angle and its opposite side. But because we have two angles, we can find this third angle because the three angles have to add up to equal 180 degrees. So if I took the 180, subtract the two angles that were given, that helps me find the third angle. And so now we have our angle and its opposite side. So if we begin to apply this as an example, here's the first example. In this example, we're working with an SAA situation. You're given a side, an angle, and another angle. So they're asking you to find AC. So we're trying to find AC. AC just happens to be opposite of angle B. So we'll label it lowercase b. The other bits of information given to us was this angle A and the opposite side. So again, we'll label it little a. So now we can create our law of sines ratio. One thing to be aware of, because we're trying to find AC, which is a side, that means we're going to put this on top. So here's our ratio. A over sine A equals B over sine B. Substitute the values in. A was 12. Uppercase A was 18 degrees. Lowercase b is what we're trying to find. And sine of 116 was our uppercase B. So what we now have is a proportion. Back in grade school, we applied cross multiplying. So if we cross multiply, we get 12. Sine 116 equals B sine 18. Solve for B by dividing sine 18 on both sides. So the only calculation will be 12 sine 116 over sine 18. That's what I'll put into the calculator. So let me clear this. So we get 12 sine 116 all over sine 18. So put it all in the calculator. Gives us about 34.9-ish. So B, 34.9-ish. Next problem. This time this example uses ASA. We're being given we're trying to find AC. Again, AC is there, so AC will be lowercase b. We've been given an angle, and so this angle opposite of angle 38 is lowercase a. So we can begin to see we have our ratio of b's and our ratio of a's. But actually we don't, because we don't have this side here. So the deal is that this 21 here, angle C. So in this case, in order to create our ratio, we've got the b's, but we don't have a ratio of a's and we don't have a ratio of c's. So that means we actually can find the measure of angle C. By doing our subtraction from 180, C equals 54 degrees. So now we have our ratio of A's and a ratio of C's. Because we're trying to find B, we'll put it on top. Substituting the values in. Sine 88, there's our angle B. 21 is C. Sine 54, there's our C. Again, cross multiply. Solve for B by dividing sine 54 on both sides. B is equal to 21 sine 88 over sine 54. That's what we put into a calculator. So we clear this again. That gives us 21 sine 88 over sine 54. There we go, 2594-ish. So B equals to 25.9 miles, approximately. Third example. Here we're trying to find the measure of angle C. So opposite of angle C was our 8, so there's our ratio. And we have angle A here, opposite of that, lowercase a. So we've got enough ratios to create our sine. Because we're trying to find the measure of angle C, that's what we put on top. Substituting the values in, again, cross multiply, yields the 8 sine 89 equals 16 sine C. In this case, we've got to divide by 16 on both sides. So this is what we're putting into the calculator. Here we got a couple extra steps to do here. So when we put this into the calculator, we'll get this number here. And I'll pull it up shortly. But now we still try to find what C is. Because C is being signed, we'll have to inverse sine on both sides. So I'll illustrate what's going on in the calculator. We started off with, let's clear this, the 8 sine 89 all over 16. That tells me the sine of C. To get C by itself, so second sine. So that's my inverse sine, second answer. So I'm not going to type this in. We'll let the calculator do it. There it is, about 29.9. That's really close to about 30 degrees. So there's our inverse, about 30 degrees. One more example. Here, notice no pictures are given. So we'll have to determine how to set up the ratios by the variables given. Well, here we're given angle A and lowercase a. So there's no need to actually draw a picture. We can tell that these are opposite each other. And we've been given angle B and lowercase b. So there's our second ratio. And because we're trying to find lowercase b, we're going to put this on top. So our ratio, lowercase a over sine a equals lowercase b over sine b. So again, there's no need to actually draw the illustration. So let's go ahead and substitute the values in. Again, cross multiply. To get b by itself, we'll divide sine 27 on both sides. Sine 27's cancel. This is what we put into the calculator. Let's clear that, and we get, what's that? 15 sine 31 over sine 27. There's our B. A little bit around 17, what is this, meters. 17 meters. So there we go.